We've been drawing Lewis structures, but it's easy to make mistakes. How can we spot mistakes? And if we have resonance, are some structures better than others? In judging the quality of the Lewis structures we have drawn, there are a few things we should routinely check to see if we've made a mistake. We should check to see that all atoms obey the octet rule. Assuming that we are using the shared pair formula correctly, have we shown the correct number of shared pairs? And have we shown the correct number of total electrons in the structure? This should be the same as the number of valence electrons we computed in the shared pair formula. Take a look at this structure, where we're told that no lone pairs exist in the molecule. What atoms violate the octet rule? We're looking for hydrogen atoms that have more than 2 electrons and carbon atoms that have more or less than 8. There would be 4 atoms that violate the octet rule. Of all the hydrogen atoms, they all have single bonds as expected, except for the hydrogen on the left. H's never have double bonds. The carbon on the left has 3 single bonds and a double bond. That would be 10 electrons. The second carbon has 3 single bonds, which is only 6 electrons. The third carbon again has 10 electrons around it. Since we are always using the octet rule in this course, being able to see atoms that violate it is useful. Take a look at these 4 structures for hydrogen cyanide and see if you can find things wrong about them. First, do any violate the octet rule? In A, the hydrogen is shown with a double bond, so that is not a good structure. In C, the nitrogen at the right has only 6 electrons around it, so A and C would not be good quality structures. Using the shared pair formula, the structure should show 4 shared pairs. A and B have 4 shared pairs, but C and D do not, so they would not be good quality structures by the shared pair rule. What about the total number of electrons shown? VE is 10 in this case. B and C show 10 electrons, but A and D show 12. Thus, A and D are not good quality structures by the valence electron rule. What you see here is that if there's one thing wrong about a structure, there is usually more than one thing wrong. Can you find anything wrong with these structures of the nitrite ion? Looking carefully at all of the atoms, they all obey the octet rule, so there is no distinction there. The shared pair formula works out to 3 shared pairs and 18 valence electrons. Only structure A has that. Structure B shows 4 shared pairs and 16 valence electrons. Structure C shows 2 shared pairs and 20 valence electrons. Again, we see that B and C have 2 things wrong with them. If we have multiple resonance structures that obey the octet rule and have the correct number of shared pairs and total electrons, there may still be a reason to prefer one over others based on formal charge. There are 2 rules of thumb that we can apply. First, the best structures have formal charges that are closest to 0. Non-zero formal charges suggest that charges have been separated, which always requires energy. The bigger the formal charges, either positive or negative, the poorer the structures. If there are formal charges, better structures will have negative formal charges on the most electronegative atom. This makes sense, since electronegativity is a measure of the ability to attract negative charge. Here are 2 resonance structures of sulfur dioxide. They both satisfy the octet rule and show 3 shared pairs and 18 electrons overall. They each have a positive formal charge on sulfur and a negative formal charge on a terminal oxygen. These 2 structures are truly equivalent. Here are 2 resonance structures of carbon dioxide. Note that there would be a third structure where there would be a triple bond to the right-hand oxygen atom. Again, they both obey the octet rule and have the proper number of shared pairs and valence electrons. The structure on the left has no formal charge, whereas the structure on the right has formal charges on the oxygen atoms. In this case, the structures are not equivalent. The one on the left is good, while the one on the right is poor. Resonance is present in carbon dioxide, but only one of the three total resonance structures is good. In this case, we would determine the bond order from the good structure. Finally, we come to the idea of shape. When we talked about ozone, we had three possible structures. The top two have formal charges, whereas the bottom triangular structure doesn't. So it might be tempting to think the triangle is the best structure. However, we know that the interior angles of an equilateral triangle are 60 degrees. This type of angle between bonds is rare. There are a few examples, but generally we would rule this structure out on the basis of angle. But we might ask, what are the angles suggested by the other two structures? After all, Lewis structures are two-dimensional drawings, but molecules live in a three-dimensional world. That question leads us to our next module, where we will consider the shapes of molecules.